Right now, on May 1st, a Texas resident is pulling a jacket out of a closet they already packed away for summer. At the exact same moment, someone in Seattle is looking up the nearest beach. Same country, same weekend, same single storm system doing both. That's not a coincidence, that's a symptom. And here's the thing nobody's connecting on the morning shows. The same machine that froze Texas and cooked Seattle last week threw an EF-borne tornado at Oklahoma. This week it's flooding the Gulf Coast. Next week, forecasters are already pointing at a potential Dixie Alley outbreak. One locked pattern, multiple disasters on a timer, and it is not done. Stay with me, because what this system is actually building toward in May is the part nobody's talking about yet. If this already has you asking questions, hit like and subscribe to the Skylab, because this story is nowhere near finished. The pattern is still locked. The events are still compounding. Forecasters are still watching the next round load up in real time. And the deeper you go into what this atmospheric machine is actually building toward, the more important it becomes to have someone connecting the dots. That is exactly what you will want to be here for when the next piece of this drops. Now let us get into it. Part 1. The claim. One machine, multiple extremes. The first thing you need to understand about what's happening across the United States right now is that it's not happening in pieces. It's not Texas having a cold snap while Seattle has a heat wave, while Louisiana floods, while Iowa freezes. That framing is wrong. That framing is what most of the morning shows are giving you, because it's easier to pull off a 3-minute weather hit when you treat each region as a separate story. But these aren't separate stories. They're the same story, told in different dialects by the same atmospheric machine. Let's start with Texas, because the numbers there are genuinely strange. We're talking about daytime high temperatures forecast to land in the 50s across a state that, on May 1st, normally sees afternoon readings in the 80s. That's a 15 to 30 degree Fahrenheit departure from normal, not for an overnight low, which is what you usually see when cold records get challenged in spring, but for the daytime maximum, the hottest part of the day, in one of the hottest states in the country, behaving like a damp afternoon in November. People in Dallas are pulling jackets out of closets they thought they'd already packed away for the season. Restaurant patios are empty. Air conditioning units that hummed to life 2 weeks ago are sitting silent again. Now drag your eyes northwest, 1,500 miles, to the Pacific Northwest. Seattle is closing in on 81 degrees Fahrenheit, which doesn't sound dramatic until you understand that the previous record for this weekend has held since the mid-1990s. People are at the beach in Washington state. In Texas, they're running the heater. And both things are being driven by the same atmospheric system. This is what meteorologists call a continental scale temperature dipole. Two opposing extremes, locked into place at opposite ends of the country, generated by a single distortion in the upper atmosphere. It's not coincidence. It's not weather doing what weather does. It's a structural output of a specific, identifiable pattern in the jet stream, and that pattern has decided, for reasons we'll get into, that it's not going anywhere. But the dipole is just the most visible symptom. Underneath it, the same system is generating other extremes simultaneously. Down along the Gulf Coast, from Houston through New Orleans and into the Florida Panhandle, the National Weather Service has approximately 65 active flood warnings posted right now. That's not flash flood watches, which are advisory level products. Those are warnings, meaning flooding is either occurring or imminent, and people need to take action. Rivers are rising. Bayous are spilling out of their banks. Streets in low-lying neighborhoods are filling with brown water that smells like swamp. At the same time, freeze warnings are stretching across a corridor from the upper Midwest, through the Great Lakes region, and down into parts of the Mid-Atlantic. We're talking about Iowa, Wisconsin, Michigan, Ohio, Pennsylvania. Places where corn was planted 3 weeks ago. Places where fruit trees are in bloom. Places where overnight low temperatures are about to drop into the mid-20s Fahrenheit, which is the kind of cold that doesn't just stress crops, it kills them outright. So let me lay this out for you, because I want you to feel the weight of it. At this exact moment, in a single country, the atmosphere is producing record cold, record warmth, major flooding, and agricultural freeze conditions, all at the same time. That combination is genuinely rare. The National Weather Service has been keeping records for over a century, and the number of days when you can find that complete suite of hazards active simultaneously across that geographic spread can probably be counted on your fingers and toes. And here's the part that should make you sit up. This isn't even the worst day of this pattern. The worst day already happened last week. Between April 23rd and April 28th, the same system that's producing today's contradictions unleashed what I can only describe as a marathon of destruction across the central United States. 97 tornado reports filed with the Storm Prediction Center over 6 days. Most of those came in clusters, long lines of supercells that walked across the plains and the Mississippi Valley, dropping twisters one after another, like a manufacturer testing a new product line. The headline event was an EF4 in Enid, Oklahoma, winds estimated at 170 miles per hour, a tornado strong enough to scour grass off the ground and bend rebar like wet spaghetti. There was an EF3 in Mineral Wells, Texas, an EF2 in Runaway Bay that killed people, hailstones the size of softballs, multiple reports, of hailstones 5 inches in diameter. That outbreak alone would have been the meteorological story of the spring in a normal year. But it's not the story, it's a chapter, it's part 1. The operational stress this pattern is putting on the National Weather Service is something I don't think most people appreciate. Over those 6 days of severe weather, the agency issued more than 1,500 warnings, tornado warnings, severe thunderstorm warnings, flash flood warnings across dozens of forecast offices. Forecasters were working 16-hour shifts. Radar operators were swapping out mid-watch because the cognitive load of tracking that many simultaneous threats burns people out faster than any other job in atmospheric science. And forecasters are already telling us, in their official discussions, that they expect this to continue into mid-May. They're not hoping it'll calm down, they're planning for it not to. So here's the question I want to plant in your mind, the one that's going to drive everything else we talk about in the next hour. If this system has already escalated once, if it has already produced an EF4 and 97 tornadoes and over 1,500 warnings, is it now stabilizing? Is it winding down the way most severe weather episodes do after their first major release of energy? Or is it doing something else? Is it, in fact, reloading? Because there's a metric buried in last week's data that almost nobody is talking about. And once you see it, you can't unsee it. It changes how you read everything that's happened since. Part 2. The data spike most people missed. I want to talk about a number that didn't make the headlines. It should have, but it didn't, because it's the kind of number that only means something to people who already know how the National Weather Service works. 95 warnings. In one day, from a single forecast office. The office is in St. Louis, Missouri. It covers a chunk of eastern Missouri and southern Illinois, a fairly typical mid-sized forecast area, the kind of region you'd expect to see maybe a dozen warnings on a busy severe weather day. 20 would be a serious outbreak, 40 would be exceptional, 95 is something else entirely. 95 is the kind of number that makes meteorologists at other offices pick up the phone and ask their colleagues if they're okay. To put this in context, that's the highest single-day warning total ever recorded out of that office, going back through their archives to at least 1986. We're talking about 40 years of records, 40 years of severe weather seasons, including some genuinely historic ones, the 1999 tornado outbreak, the May 2003 sequence, the April 2011 super outbreak, the December 2021 quad state event. None of those generated 95 warnings in 24 hours from St. Louis. This one did, and here's why that matters. A single warning isn't really a measure of severity, but a daily warning count is something different. It's a measure of system intensity over time. It tells you how relentlessly the atmosphere is producing dangerous storms in a given area. Most outbreaks have a peak 3 or 4 hours where everything is firing at once, and then a wind down. Forecasters call this the operational tempo, and even violent outbreaks usually give the office staff a break by sunset. The storms move out of the area, the warm sector retreats, the radar goes quiet for a while. That's not what happened in St. Louis. The atmosphere in their forecast area cycled storms continuously for almost the entire day. Cells would form, mature, drop hail, and produce rotation, then dissipate, and within 20 minutes, new cells were forming on the same boundary. The system never gave the office a recovery window. The radar never went quiet. The warnings just kept coming. This is what I mean by warning saturation, and it's a system-level stress signal that tells us something specific about the atmospheric driver. Episodic outbreaks, the kind we usually see, are produced by transient features. A short wave moves through, ignites a few hours of severe weather, and then exits. The atmosphere essentially fires a single round and then has to reload before it can fire again. But what happened in St. Louis wasn't a single round. It was a sustained discharge. The atmospheric forcing didn't pulse through. It parked overhead and kept feeding the storms. That kind of sustained forcing requires something in the upper levels to be holding still. A persistent feature, a stalled trough, a locked ridge, a closed low has to be sitting in just the right position to keep funneling instability and shear into the same geographic area for hours on end. And that, right there, is the fingerprint of the same locked atmospheric pattern that's now producing the temperature dipole and the Gulf flooding and the freeze warnings. The St. Louis warning surge wasn't a freak event in isolation. It was the first measurable output of a system that hasn't stopped running since. Across the entire 6-day outbreak, the broader numbers tell the same story. 97 tornado reports, more than 1,000 reports of severe hail, over 800 reports of damaging wind, spread across multiple states, multiple days, multiple rounds of activation. This wasn't one storm, it wasn't one outbreak in the traditional sense. It was the atmosphere maintaining elevated severe weather output for almost a full week. Here's the insight I want you to hold on to. The atmosphere didn't spike. It didn't flash up to severe levels and then come back down. It rose to a high baseline and stayed there. And as we sit here today, on May 1st, that baseline has not actually returned to normal. The flavor of the weather has changed. We've shifted from severe storms over the plains to flooding on the Gulf and dipole extremes nationally, but the underlying intensity hasn't budged. The atmosphere is still operating at elevated output. It's just expressing it differently this week, which raises an uncomfortable question that I want you to start chewing on. If the system stayed elevated through last week's outbreak, and it's still elevated this week, and the Climate Prediction Center is forecasting it to remain elevated through mid-May, at what point does this stop being a weather event and start being something else entirely? Hold that thought, because to really understand what we're looking at, we need to talk about the dipole itself, and why it's not just an unusual coincidence. Part 3: the dipole as a signature, not an anomaly. When you see a temperature contrast like the one currently splitting the United States, 50s in Texas, 80s in Seattle, on the same calendar day, there's a tendency in popular weather coverage to treat it as a kind of fluke, two unrelated extremes that happen to be occurring at the same time. The cold air is doing its thing, the warm air is doing its thing. They just happen to be doing those things simultaneously. And isn't that a strange coincidence? That framing is wrong. It misunderstands the basic geometry of the atmosphere. The temperature dipole isn't a coincidence. It's a signature. It's the structural output of a specific configuration of the jet stream. And once you understand the geometry, you'll never look at a continental temperature contrast the same way again. Think of the jet stream not as a single river of fast-moving air, but as a wavy ribbon that wraps around the northern hemisphere. Most of the time, that ribbon is reasonably flat. It dips a little here, rises a little there, and the waves move steadily eastward, carrying weather systems with them at a brisk clip. Meteorologists call this zonal flow, and it's what produces the boring, progressive, normal weather that most of us don't pay much attention to. Cool morning, warm afternoon, scattered showers, repeat. But sometimes that ribbon gets distorted, the waves get bigger. They start dipping further south and rising further north, a low-slung trough, plunging deep into the southern states. a towering ridge bulging up into Alaska or Western Canada. When the wave amplitude gets big enough, the ribbon stops moving in the smooth east-west direction it normally takes and starts moving more in a north-south direction. Air that should be flowing west to east is now flowing north to south on one side of the wave and south to north on the other. That's exactly what's happening right now. We have a deep trough, anchored in the upper Midwest and Great Lakes region, that's reaching all the way down to the Gulf of Mexico. On the western side of that trough, the jet stream is pulling Arctic air down out of central Canada and shoving it into Texas. That's why Texas is in the 50s. The state isn't manufacturing cold, it's being delivered cold from 1,000 miles north by an atmospheric flow that's pointing the wrong direction for early May. Meanwhile, on the upstream side of the same wave, over western North America, there's a corresponding ridge, a bulge of high pressure that's pushing the jet stream way up into northern Canada. On the eastern side of that ridge, the flow is going from south to north, pulling subtropical air all the way up the Pacific coast into Washington state. That's why Seattle is at 81. It's not a local heat wave. It's tropical air being chauffeured north by a jet stream that's bent into a shape that allows it to happen. So when you see the temperature contrast 30 degrees Fahrenheit difference across the continent, you're not seeing two events. You're seeing one event with two faces. The cold in Texas and the heat in Seattle are mathematically required to coexist given the shape of the jet stream. You can't have one without the other, and here's where it gets really interesting. There's a historical analogue for this kind of pattern, but it's not a perfect match. May 2020 produced a similar continental dipole with very cold air invading the eastern half of the country while the west baked. But that pattern lasted maybe 4 or 5 days before the jet stream relaxed and progressive flow resumed. What we're seeing now is on track to last significantly longer than that, and the amplitude of the wave is greater. The cold side is reaching further south, and the warm side is reaching further north than the 2020 event managed. There's another anomaly buried inside this dipole that's worth pulling out separately. When you set cold weather records in the spring, the records that usually fall are overnight low temperatures. The atmosphere cools off after sunset, and on a clear, dry night with light winds, you can occasionally drop a degree or two below a previous record. Those records are common. They happen somewhere in the country almost every week of the cool season. But the records being challenged in Texas this weekend aren't overnight lows. They're daytime high temperature records, the lowest daytime maximum ever recorded for that date. That's a much rarer category. It requires the atmosphere to stay cold not just at night, but through the entire daytime heating cycle. It requires thick cloud cover, cold advection from the north, and a sun angle that isn't strong enough to overcome the cold air mass. To set a record low daytime high in Texas in May, the atmospheric forcing has to be intense, persistent, and pointed in a very specific direction. It doesn't happen by accident. This brings us to a concept I want you to remember, because it's going to come back several times in this video. It's called baroclinic gradient amplification. Stripped of the jargon, it just means that the bigger the temperature contrast across a horizontal distance, the more energy is available to drive storms along the boundary between the two air masses. The dipole isn't just creating temperature extremes, it's creating an unusually sharp temperature gradient running diagonally across the country, from the cold sector in the southern plains up through the warm sector in the west. And that gradient is the fuel tank for everything else this pattern is producing. The flooding on the Gulf Coast, that's happening because the moisture-rich warm sector is colliding with the cold sector along the southern edge of the trough, forcing massive amounts of water vapor to condense and fall as rain. The severe storm risk for next week, that's powered by the same gradient, the same energy contrast, the same sharp boundary between competing air masses. Even the freeze conditions in the Midwest are a product of the dipole, because the same flow that's dragging cold air into Texas is also pulling it up into the Great Lakes region behind the trough. So when meteorologists describe this as a heat pump in reverse, they're being more precise than they sound. A normal heat pump moves heat from outside to inside, or vice versa, by exploiting a gradient. The atmospheric configuration we have right now is doing something similar at continental scale. It's exploiting the temperature gradient between Arctic Canada and the subtropical Pacific, and using the energy of that gradient to drive every other extreme we're seeing: cold, heat, flood, severe storm, and freeze. 5 different hazards, 1 pump, 1 pattern, which is why I want to come back to the central question before we move on. The dipole isn't a curiosity. It's not a strange weekend story you'll forget about by Tuesday. It's the visible fingerprint of an atmospheric system that's holding still, and the question we have to answer is what happens when a system this powerful refuses to move. Because the longer it stays parked, the more energy it accumulates, and the more energy it accumulates, the more dangerous each release becomes. And there's one more piece of evidence that this isn't a transient pattern. It's a piece of evidence that involves the wrong season showing up in the wrong place, and it has agriculture economists very, very nervous. Part 4, the out-of-season red flag. The freeze warnings strung across the upper Midwest, the Great Lakes, and into the mid-Atlantic right now are the kind of detail that gets buried in the bottom of weather reports because they don't sound dramatic. Freeze warnings happen all the time. Most people, hearing about a freeze warning, think about covering tomato plants in the backyard and move on with their day. But freeze warnings in the first week of May, across that geographic spread, are statistically rare to a degree that should make you pay attention. Climatologically, an early May freeze across that corridor sits in the upper decile of historical records, meaning it's something that happens, on average, less than 10% of the time. In some of those locations, like central Ohio and southeastern Michigan, the historical odds of a freeze warning being issued on May 1st are closer to 3 or 4%. We're not talking about an unusual cold snap. We're talking about an event that, in any given year, has roughly the same probability as flipping a coin and getting heads 4 times in a row. And that's just the temperature side. The agricultural impact is where it really starts to get serious, because crops in early May aren't dormant. They're not safely tucked away underground waiting for warmth. They're up. They're growing. Across most of the Corn Belt, planting wrapped up in mid to late April, and the seedlings are now somewhere in the V1 to V2 growth stage, meaning they've put out their first or second true leaves. At that stage, corn can tolerate brief dips into the upper 20s Fahrenheit, but sustained exposure to mid-20s for several hours overnight can damage or kill the growing point. And the growing point, once damaged, doesn't come back. The plant either dies or recovers as a stunted, low-yield version of itself. The forecast lows for parts of Iowa and Nebraska this weekend are running into the mid-20s Fahrenheit. Some inland valleys could see readings in the low 20s. Fruit trees in Michigan and northern Ohio are in bloom, which is the most cold-sensitive stage of the entire growing season. A single hard freeze at full bloom can destroy an entire year's apple or cherry crop in a region. Ask anyone in Michigan about 2012, when an early warm spell followed by a late freeze wiped out essentially the entire state's fruit harvest. The conditions setting up this weekend look uncomfortably similar. But there's something else going on with this freeze that I want to draw out, because it connects directly to the central question of this video. Cold weather in March is one thing. Infrastructure is set up for it. Farmers haven't planted yet. Pipes are still insulated. Heating systems are still running. The whole country is structurally prepared for cold to happen, even cold that's a little out of the ordinary. Cold weather in May is a different category of problem. The infrastructure has been transitioned out of cold mode. Heating systems have been serviced and shut down. Pipes that were drained for the winter have been refilled. Farmers have planted, paid for seed and fuel, and committed their entire growing season to the assumption that the threat of frost is past. When cold shows up in May, it doesn't just damage crops, it catches an entire region with its guard down. The systemic mismatch between what the calendar implies and what the atmosphere is delivering creates economic damage that goes far beyond the temperature reading itself. Historically, you have to look at specific analog years to find anything comparable. May 2005 had a late-season cold outbreak that affected the eastern Corn Belt. May 1989 produced freeze conditions across the Midwest that knocked back wheat yields in several states. but both of those events were briefer and less geographically widespread than what we're seeing this weekend. The current setup is delivering freeze warnings across a corridor that stretches from Nebraska all the way into the mid-Atlantic. That's a geographic spread of more than 1,000 miles, all under simultaneous freeze threat in the first week of May. And here's why this matters for our central thread. The temporal anomaly cold at the wrong time of year is one of the strongest indicators that the underlying pattern is not transient. Brief cold snaps in May are usually produced by passing short waves, weak features that move through quickly and dump cold air briefly before progressing east and getting absorbed. What we're seeing instead is sustained cold advection over multiple days, which requires the source region Arctic Canada to be connected to the target region, the upper Midwest, by a stable pipeline of north-south flow. That pipeline is the western side of the locked trough. As long as the trough holds its position, the pipeline keeps delivering cold. And the cold is exactly the kind of evidence forecasters use to confirm that the upper-level pattern is anchored, not drifting. So the freeze warnings aren't just a hazard story, they're a diagnostic. They're telling us with high confidence that the atmospheric machine driving everything else we've talked about is locked into position and not showing signs of breaking down. The wrong season showing up in the wrong place, across the wrong geography, isn't a quirky weather story. It's the second piece of physical evidence after the dipole itself that what we're dealing with is a deeply anchored configuration, which makes the next thing I want to talk about even more sobering. Because if the pattern we have now is sustained and reloading, then last week's outbreak wasn't the climax of this story. It was the prologue. Part 5, the first release of energy, already happened. Let's go back to those 6 days, April 23rd through April 28th, with what we now know about the pattern that produced them. Because in retrospect, that outbreak wasn't a one-off severe weather episode. It was the first major energy release from a system that has not stopped charging. The numbers, when you really sit with them, are extraordinary. 97 tornado reports across 6 days. To give you a sense of scale, the average for the entire month of April across the United States is somewhere around 200 to 250 tornadoes. We hit nearly half of that monthly average in less than a week. The tornadoes weren't scattered randomly across the country either. They clustered in a corridor running from the southern plains through the Ozarks and into the Mississippi Valley, a geographic pattern that exactly traces the southern edge of the upper-level trough we now know was driving the whole thing. The headline tornado was the EF4 in Enid, Oklahoma, estimated peak winds of 170 miles per hour. An EF4 is the second highest rating on the scale, just below the rare EF5 category, and it's strong enough to do things that defy intuition. Rebar gets twisted into shapes that look intentional. Concrete foundations get scoured down to bare aggregate. Cars get thrown distances measured in hundreds of yards, not feet. The Enid tornado was on the ground long enough to walk through residential neighborhoods, and it took out homes that had been built to current code, with the kind of destruction that makes engineers re-evaluate what current code means. The Mineral Wells, Texas tornado was rated EF3 with estimated winds of 150 miles per hour, also on the ground long enough to cause significant structural damage. The Runaway Bay tornado was rated EF2, weaker on paper, but it killed people, which is the only measure of a tornado that ultimately matters: multiple fatalities. A small lakeside community in North Texas, where the warning lead time, even with the best technology and protocols available, wasn't enough to save everyone in its path. But the tornado numbers, as terrible as they are, don't capture the full picture of last week's atmospheric output. The hail reports tell their own story. More than 1,000 reports of severe hail, meaning hail at least 1 inch in diameter across the 6-day period. Inside that 1,000, there were dozens of reports of giant hail, 2 inches or larger. There were reports of softball-sized hail, around 4 inches. There were a handful of reports of hailstones 5 inches in diameter, which is in the top fraction of 1% of all hail ever observed in the United States. Hail that big falls at terminal velocities approaching 100 miles per hour, It doesn't dent a car roof, it punches through it. The wind reports added another 800+ events to the database. Severe wind, by the National Weather Service definition, means gusts of 58 miles per hour or stronger. Many of last week's wind reports were significantly above that threshold, with gusts exceeding 70 and 80 miles per hour reported across multiple states. Power infrastructure took major hits. Transmission towers came down. Trees that had survived decades of normal storms got snapped or uprooted in regions where forests are accustomed to weather. Now, I want to come back to that St. Louis warning anomaly because it fits into this larger picture in a way that's worth understanding. 95 warnings in a single day from one office. When you cross-reference that with the geographic distribution of last week's tornadoes, you find that the St. Louis forecast area sat almost exactly under the eastern flank of the upper-level trough during the peak of the outbreak. The atmospheric forcing in their area was being generated by the strongest part of the pattern, the curvature in the jet stream, where the trough started to bend back to the east. That bend is a known severe weather amplifier, and it sat over Missouri and Illinois for almost a full diurnal cycle. Here's something that I want to flag, though, because it's important and it's also a little uncomfortable. Last week's outbreak, despite its intensity, produced a relatively low fatality count compared to what the meteorological setup might have suggested was possible. We had a violent EF4. We had multiple long-track tornadoes through populated areas. The total death toll is genuinely smaller than what historical analogues would have predicted. That's partly a testament to improved warning systems, better building codes in some areas, and broader public awareness of what to do when a tornado warning is issued. It's partly luck. Several of the worst tornadoes happen to track through less densely populated areas, and it's partly that the outbreak occurred over a full 6 days rather than concentrated into a single afternoon, which gave forecasters more lead time on individual events. But that low fatality count creates a dangerous narrative. There's a temptation, when an outbreak doesn't produce the death toll people were braced for, to file it away as a near miss and move on. And the problem with that filing is that it underestimates the system that produced it. The atmosphere didn't pull its punches last week. It threw everything it had. We just happened to dodge most of it. If the same pattern reloads and produces a similar outbreak, the dodge factor doesn't carry over. Each new event is its own roll of the dice. And here's the part that connects this back to where we are right now, on May 1st. The flooding currently underway on the Gulf Coast is happening along the same baroclinic boundary that powered last week's tornadoes. The instability gradient, the moisture feed, the upper level forcing all the same ingredients, just expressing differently because the boundary has shifted south. The system that produced last week's outbreak hasn't dissipated. It hasn't even significantly weakened. It's just changed modes. The framing I want you to take away from this section is that April 23rd through 28th was not the peak output of this pattern. It was the first discharge. The atmosphere ran one cycle, vented some of its accumulated energy, and is now charging up for the next one. Forecasters are watching that next charge build right now, in real time, in their model output and their satellite imagery and their upper air observations. And the question of what it does next is no longer a question of if it will produce another major event. It's a question of when and where and how big. The system that produced last week's outbreak has not dissipated. So what is actually keeping it locked in place? Part 6. The Rossby Wave Lock. To understand why this pattern won't move, you need to picture the atmosphere not as a collection of weather systems, but as a single global flow of air, distorted into waves, wrapping around the planet at upper levels. Those waves have a name. They're called Rossby waves, after the Swedish-American meteorologist Carl Gustaf Rossby, who first described their behavior in the 1930s. Rossby waves are huge, planetary-scale undulations in the upper atmosphere, and they're the reason weather happens at all. Without them, the atmosphere would be a smooth, boring conveyor belt, with cold polar air staying near the poles and warm tropical air staying near the tropics, and nothing interesting in between. Rossby waves are what mix the system up. Their troughs reach down toward the equator, dragging cold polar air south. Their ridges push up toward the poles, pulling warm tropical air north. Every weather system you've ever experienced is, in some sense, a feature embedded in or generated by these waves. Most of the time, Rossby waves move. They have a characteristic phase speed, the rate at which the troughs and ridges progress eastward, and that speed is usually fast enough that any given location only sees a particular wave feature for a day or two before it slides onto the next region. The progression is what gives us the rhythm of normal weather. Cold front, warm front, brief storm, clearing, repeat. But the speed of Rossby waves isn't constant. It depends on a few things. The wavelength of the wave, longer waves move slower, the strength of the underlying winds, and the meridional position of the wave. And under certain specific conditions, the phase speed can drop to almost zero. The waves stop moving, they lock into position. And whatever weather features are embedded in them, the troughs, the ridges, the closed lows, sit in place for days or weeks at a time. That's what's happening right now. We have a high-amplitude Rossby wave configuration locked across North America. The trough I mentioned earlier, the one anchored over the Great Lakes and extending down through the central United States, is the bottom half of this wave. The ridge over western North America is the top half, and the entire structure has slowed to a phase speed close to zero. It's holding its position with remarkable stability. The way meteorologists describe this is by saying the pattern has gone into a meridional flow regime as opposed to the more typical zonal flow. Zonal flow is when the jet stream is mostly running east-west with small ripples. Meridional flow is when the jet stream is running strongly north-south over big sections of the continent, because the wave amplitude has gotten so large that the flow is mostly oriented along the meridians, the lines of longitude, instead of along the parallels of latitude. Meridional flow is what produces extreme weather. It's what dredges Arctic air down into the south and pushes tropical air up into the north. And when meridional flow gets stuck, you get exactly what we're experiencing. There's a specific feature inside this configuration that's acting as the anchor for the whole thing. It's called a closed low, and it's currently parked somewhere in the upper Midwest, embedded in the deepest part of the trough. A closed low is what happens when the trough wraps so far around itself that it pinches off into a self-contained circulation, almost like an upper-level eddy. Once a closed low forms, it becomes essentially independent of the surrounding flow. Other weather systems flow around it instead of pushing it along. It can sit in one place for days, drifting only slowly, while the rest of the atmosphere reorganizes itself around its presence. The analogy I find useful is a conveyor belt that's stuck. Imagine a factory conveyor belt that's supposed to be moving products from one end to the other. Most of the time, it works smoothly. Products go in one side, come out the other. But if something gets jammed in the mechanism, the belt stops moving. The products that were already on it just sit there. And meanwhile, the supply line keeps feeding more material onto the stuck belt, piling it up in one place. That's roughly what's happening with the atmosphere right now. The Rossby wave isn't progressing, but the atmosphere keeps generating new energy and feeding it into the same stuck configuration. The temperature gradients keep sharpening. The moisture keeps pooling along the southern edge. The instability keeps building. And every so often, a piece of that stuck system breaks loose and produces severe weather, but the underlying configuration doesn't change. There's a question that probably occurred to you at some point during all this. What's holding the wave in place? Why doesn't it just resume normal eastward progression the way Rossby waves usually do? The answer involves a feedback loop, and it's where the science gets really interesting. When a Rossby wave amplifies, meaning the troughs get deeper and the ridges get taller, it changes the dynamics that govern its own movement. Bigger waves move slower than smaller waves, all else being equal. So as the wave amplifies, it inherently slows down. That gives it more time to amplify further, because the upstream forcing has more time to push energy into it before it slides east. The slower it goes, the more it amplifies. The more it amplifies, the slower it goes. Eventually, this feedback can drive the phase speed all the way to zero, and the wave locks. Once locked, only a major change in the upstream forcing can break it free. This is what we mean when we say the pattern is locked. It's not just sitting there inertly, it's actively reinforcing itself. The deep trough is pulling cold air south, which sharpens the temperature gradient, which strengthens the jet stream around the wave, which deepens the trough further. The ridge is pulling warm air north, which strengthens the high pressure aloft, which builds the ridge taller, which feeds the trough downstream. Every component of the system is pumping energy into every other component. The atmosphere has found a stable, high-amplitude configuration, and it's not going to let go easily. The persistence is the key anomaly here. We see high-amplitude patterns occasionally. They're called blocking patterns when they really lock in, but they usually break down within 5 to 7 days as upstream perturbations finally accumulate enough force to disrupt the configuration. What we have now is showing every indication of lasting longer than that. Forecast models are showing the pattern holding through at least mid-May, which would put the total duration at well over 2 weeks. That's the kind of persistence that pushes a pattern from unusual into genuinely rare. And here's the part that's going to set up the next section. The persistence isn't just being maintained by the internal dynamics of the wave itself. There are external influences supporting the pattern features in the broader atmospheric system that are reinforcing the locked configuration from the outside. Without them, the wave might break down on its normal timescale. With them, it has support. And those external influences are about to make this story significantly more interesting. Part 7. The Hidden Reinforcement Layer. The atmospheric pattern over North America isn't operating in isolation. It's connected to the rest of the planet, and the rest of the planet is currently providing it with reinforcement. There are 2 large-scale climate features that meteorologists track when they're trying to forecast pattern persistence. The first is the Madden-Julian Oscillation, usually abbreviated MJO. The MJO is a slow-moving disturbance in the tropical atmosphere specifically, an envelope of enhanced thunderstorm activity that travels eastward around the equator over a period of 30 to 60 days. As the MJO moves through different geographic phases, it sends out atmospheric ripples that can influence weather patterns far outside the tropics, including over North America. Right now, the MJO is in a phase that historically favors troughing over the central and eastern United States. Specifically, when the MJO sits in what forecasters call phases 6 and 7, meaning the active thunderstorm region is over the Pacific Ocean, the atmospheric response over North America tends to amplify the kind of high-amplitude wave pattern we're currently experiencing. The mechanism involves something called Rossby wave dispersion. When the MJO produces enhanced tropical convection in a particular geographic region, that convection releases latent heat at high altitudes. The release of that heat creates ripples in the upper atmosphere, Rossby waves that propagate northward and eastward, eventually arriving in the extratropical zone, where they can interact with and reinforce existing patterns. It's a process meteorologists sometimes describe as tropical to extratropical energy transfer, and the timing of the current MJO phase is unusually well aligned with the North American pattern. The tropical disturbance is producing waves that, when they reach North America, happen to be in a configuration that supports, rather than disrupts, the locked Rossby wave we already have in place. It's like the Pacific is throwing a series of small but well-aimed punches at the North American atmospheric configuration, and every punch is landing in exactly the right spot to reinforce the pattern we already have. The second large-scale feature is something called the Pacific North American Pattern, abbreviated PNA. The PNA is a measure of the wave configuration over the Pacific Ocean and North America, and it's described by an index that can be positive or negative depending on the orientation of the waves. A positive PNA means there's a ridge over the western part of North America and a trough over the eastern part, exactly the configuration we have right now. A negative PNA would mean the opposite arrangement, with a trough in the west and a ridge in the east. The current PNA is strongly positive and has been for several weeks. That's not just descriptive. The positive PNA is dynamically supporting the pattern by keeping the western ridge anchored and reinforcing the trough in the east. The PNA tends to be more persistent than the MGO. It can hold a particular phase for weeks or even months at a time, and a positive PNA episode lasting through May would essentially guarantee that the locked pattern can't easily break down because the broader Pacific configuration that's feeding it isn't going to change. When you put the MJO and the PNA together, you start to understand why the Climate Prediction Center is forecasting this pattern to persist. They're not just looking at the North American pattern itself, they're looking at the global support structure around it. Both major teleconnection patterns are aligned in ways that favor the maintenance of the locked Rossby wave we have in place. In statistical terms, when you have both the MJ and the PNA simultaneously supporting the same North American configuration, the probability of pattern persistence over the following 10 days runs in the range of 60 to 70%. That's high. That's much higher than the climatological baseline for any given pattern lasting that long. And it's worth pausing on how unusual this dual reinforcement actually is. The MJO and the PNA operate on different timescales in different regions through different mechanisms. They don't always align. In fact, they're frequently in conflict. The MJO can be pushing the pattern one way, while the PNA is pulling it the other way, and the result is a noisy, transient pattern that doesn't really commit to any particular configuration. What's happening right now is a relatively rare alignment, where both features happen to be supporting the same configuration at the same time. That alignment is what's giving the locked pattern its unusual longevity. This is why I've been describing what's happening as a supported configuration rather than just a pattern. There's a difference. A pattern is what we call any particular arrangement of weather features at a given moment. A configuration that's supported by external forcing is something more durable. It's an arrangement that's actively being maintained by the broader climate system. When you turn off the external forcing, the pattern can dissipate. When the forcing remains in place, the pattern persists. Right now, the forcing is in place, and there's no obvious sign that it's going away. The Climate Prediction Center's outlook reflects all of this. When the agency issues a confident extended range forecast, one that projects pattern continuation through mid-month with high probability, they're not just looking at the model output. They're looking at the dynamical reasoning behind why the models are converging on that solution. The MGO support, the PNA support, the locked Rossby wave geometry, the absence of any major upstream disturbances on the horizon, all of it adds up to a forecast that the pattern is going to keep doing what it's doing for at least another 2 weeks. And that brings us back to the central question, the one that should be sitting on your shoulders by now. If the pattern is locked and reinforced from the outside and forecast to persist, then the events we've discussed so far aren't a sequence of separate weather stories. They're the early outputs of a configuration that's still operating at full power. The April outbreak, the current dipole, the Gulf flooding, the freeze warnings, all of it is being produced by a single machine, and the machine isn't slowing down, which makes the next thing we need to understand the most important piece of the puzzle. We've talked about what the pattern is and why it's locked and what's reinforcing it, but we haven't talked about how it actually generates the storms. And that requires us to look at one specific feature embedded inside the larger configuration, the boundary where the cold air meets the warm air, because that boundary is where the energy lives. Part 8. The baroclinic engine. The single most important feature inside this whole pattern, the one that's responsible for translating the locked Rossby wave into actual ground-level chaos, is what meteorologists call the baroclinic zone. The word baroclinic sounds technical, but the concept is simple. A baroclinic zone is just a region where temperature changes sharply over a horizontal distance, where cold air sits next to warm air with very little buffer between them. That's it. Anywhere on the planet where you have a sharp horizontal temperature gradient at the surface with a corresponding gradient in the air above, you have a baroclinic zone. And baroclinic zones are where most severe weather is born, because the temperature contrast itself is a form of stored energy. Let me explain why. The atmosphere, at its most basic level, is a heat engine. It's constantly trying to redistribute heat from where there's too much of it, the tropics, the daytime side of the planet, low elevations to where there's not enough the poles, the nighttime side, high altitudes. The bigger the imbalance, the more energy is available to drive that redistribution. And when the imbalance is concentrated into a small geographic region, instead of being spread out over thousands of miles, the energy density goes up. The atmosphere has more fuel per square mile to burn through. The baroclinic zone currently draped across the central United States, along the southern edge of the locked Rossby Trough, is unusually sharp for early May. Normally, by this point in the spring, the temperature gradient between cold polar air and warm subtropical air has weakened significantly compared to what we see in winter. The poles have warmed. The mid-latitudes have warmed. The whole hemispheric temperature distribution has flattened out. Severe weather season usually peaks in late April and early May because that's when the gradient still has enough strength to drive big storms, but the moisture content of the warm sector is rising fast as the Gulf of Mexico warms up. What's different this year is that the gradient hasn't weakened on schedule. The locked Rossby wave is keeping a piece of polar air parked over the central United States, refusing to let it mix out and warm up the way it normally would by this point in the season. So we have May-level moisture in the warm sector, high dew points coming off the Gulf, plenty of low-level water vapor, combined with March-level cold in the polar air mass to the north. The contrast between those two air masses is significantly sharper than what's typical for early May, which means the baroclinic gradient is amplified, more fuel per square mile. When you combine that sharp gradient with the right wind structure aloft, you get severe weather. Specifically, you get a particular combination of two ingredients that storm researchers track obsessively. The first is something called convective available potential energy, abbreviated CAPE. CAPE is a measure of how much instability is present in the atmosphere basically, how much thermal energy a parcel of air would release if you forced it to rise from the surface to the upper troposphere. High CAPE means strong updrafts in any thunderstorms that form. The current setup has been generating CAPE values in the warm sector that exceed 3,000 to 4,000 joules per kilogram, which is solidly in the range associated with significant severe weather. The second ingredient is wind shear, the change in wind speed and direction with height. Strong shear is what allows thunderstorms to organize into rotating supercells, which are the storm structures most likely to produce tornadoes and giant hail. The locked pattern is producing very strong shear along the baroclinic zone because the jet stream is bent into a configuration that puts strong upper-level winds directly above the temperature gradient. CAPE and shear together instability and wind structure are the two essential ingredients for severe weather, and the current pattern has both of them in abundance in the same geographic location day after day. The way that translates into specific storm modes is something forecasters track closely. In the early stages of an outbreak, when the boundary is still well defined and the shear is strong, you tend to get discrete supercells isolated, rotating thunderstorms that can produce the most violent tornadoes and the largest hail. As the day progresses and the storms multiply, they often start interacting with each other, eventually merging into linear systems that can produce widespread damaging winds and embedded tornadoes, but typically don't generate the most extreme events. Last week's outbreak followed exactly this progression: discrete supercells in the afternoon, producing the EF4 in Enid and the violent hail reports, transitioning to messier convective complexes overnight. What's happening now, though, is something a little different. The boundary hasn't moved much. The same baroclinic zone that produced last week's tornadoes is still in place, still sharp, still generating high CAPE values along its warm side. But the storm mode has shifted. Instead of producing supercells, the boundary is now producing slow-moving, water-laden convective systems that train over the same areas for hours at a time. The energy is the same, the fuel is the same, but the way it's being released has changed from severe storm mode to flood mode. There's a concept I want to introduce here, because it's central to understanding how the same boundary can produce such different hazards. Meteorologists sometimes describe it as energy recycling. When a baroclinic zone is sharp and active, but the storm cells moving along it aren't dissipating quickly. The cells essentially recycle the same air mass over and over. Moisture that gets lifted and condensed in one storm doesn't fully evacuate the area before the next storm arrives. The boundary becomes a kind of perpetual motion convection machine, with new cells forming on the upstream side as soon as old cells decay on the downstream side. That's exactly what's happening on the Gulf Coast right now. The same baroclinic boundary that drove last week's tornadoes is still draped across the southern United States, but it's slowed down enough that storms are training along it rather than racing across it. The result is 2 to 3 inch per hour rainfall rates over the same neighborhoods, totals of 2 to 6 inches in localized swaths, and the 65 active flood warnings I mentioned at the start of this video. Different hazard, same boundary, same pattern. The gradient is the fuel tank. That's the line I want you to remember. The locked Rossby wave is the engine that's keeping the fuel tank full. The MJO and the PNA are the supply lines that keep the engine running. And the storms, whether they're tornadoes in Oklahoma, hailstorms in Missouri, or floods on the Gulf Coast, are just the exhaust. The same machine, burning the same fuel, producing different exhaust depending on where you happen to be standing. Which leads us to the question of why the flooding, in particular, has the potential to get so much worse before it gets better. Part 9. Why the flooding is locked in. The flooding currently underway across the Gulf Coast is being driven by a specific atmospheric process that's worth understanding in detail because it's one of the most damaging modes a baroclinic boundary can run in. The process is called training convection. The name comes from the visual analogy when a series of thunderstorm cells moves over the same geographic location, one after another, like train cars passing along a single set of tracks that's training. Each cell drops its rainfall on roughly the same neighborhoods, and the cumulative effect over 6 or 12 or 18 hours can be staggering. A single thunderstorm might drop an inch of rain. A line of training storms can drop 6. The reason training is happening right now, and the reason it's hard to forecast precisely, has to do with the alignment between the boundary and the upper level flow. When a boundary at the surface, like a cold front or a warm front or a stationary front, is oriented in roughly the same direction as the winds at the steering level of the atmosphere, around 18,000 feet up, the cells that form along that boundary tend to move along the boundary rather than across it. They follow the boundary like cars following a road, and the road keeps delivering them to the same places. The current setup has a near-perfect alignment of this kind. The baroclinic boundary draped across the Gulf Coast is oriented roughly west to east. The mid-level winds are also blowing roughly west to east. So storm cells that initiate on the boundary are moving along it instead of pushing through it, and as a result, the same neighborhoods are getting hit by multiple cells in succession. The rainfall rates we're seeing reflect this. 2 to 3 inches per hour in the heaviest cores. That's a rate that overwhelms most urban drainage systems, because storm sewers are typically designed to handle peak flows from 1 or 2 inch per hour rainfall events. When you push beyond that threshold, water starts pooling on streets, backing up into basements, and rising into structures. 3 inches per hour, sustained for 2 or 3 hours, is the kind of rainfall that turns parking lots into lakes and underpasses into death traps. The cumulative totals are even more concerning. Localized swaths along the Gulf Coast are picking up 2 to 6 inches of rain over the duration of this event, and some isolated locations are reporting higher amounts. The hardest hit areas are the ones where the training has been most persistent, with multiple cells passing over the same neighborhoods over the course of 12 to 24 hours. What makes this particularly dangerous is the slow movement of the entire system. In a normal flood event, even a major one, the convective system eventually moves out of the area. The rain stops. Floodwaters peak and start to recede. People start to recover. But when the upper level pattern is locked, which is exactly what we have, the convective system doesn't move. It just keeps cycling. New cells form upstream as fast as old cells dissipate downstream, and the rainfall just keeps coming over the same geographic footprint. There's a process meteorologists call convective regeneration that captures this dynamic. In a stagnant pattern, even after individual storm cells decay, the atmospheric conditions that produce them, the boundary, the moisture, the instability, don't go away. They reset within an hour or two, and then a new cell forms in roughly the same place. The system regenerates itself, and as long as the locked pattern keeps the broader configuration stable, the regeneration can continue for days. The flash flood warning counts coming out of National Weather Service offices along the Gulf are reflecting this regenerative dynamic. Offices in Houston, Lake Charles, New Orleans, Mobile, and Tallahassee have been issuing flash flood warnings in waves over the past several days, with new warnings going up almost as quickly as old ones expire. It's the same pattern as the St. Louis warning surge from last week: sustained operational tempo, no recovery time, continuous output. The atmosphere isn't pulsing severe weather and then resting. It's running at high output and refusing to slow down. The moisture supply that's feeding all of this comes from the Gulf of Mexico. The Gulf, in early May, is already running at sea surface temperatures in the upper 70s Fahrenheit, with some patches near 80. Warm water means high evaporation rates, which means a constant supply of water vapor flowing northward into the warm sector of the locked pattern. The warm sector is essentially a giant sponge that's been wrung out repeatedly over the past week, but as long as the Gulf keeps refilling it, the wringing can continue indefinitely. Here's where it gets really sobering. The geographic zones currently under flood warnings overlap significantly with the zones that are forecast to be at risk for severe storms next week. The same regions that are dealing with rising rivers right now are going to be dealing with damaging winds and possible tornadoes in a few days. And the soil saturation from the current flooding is going to make any subsequent rainfall events more dangerous because the ground won't be able to absorb additional water. New rain will run off immediately into already swollen streams and rivers. This is the same machine I keep coming back to, but it's running in a different mode. Same boundary, same pattern, same upper level support. But instead of throwing tornadoes, it's drowning the Gulf. And the question of which hazard mode the pattern produces in any given location depends mostly on the local atmospheric conditions at the surface, the moisture, the instability, the timing of the diurnal cycle, rather than on any change in the underlying machine. Which brings us to a question that I know is sitting in some viewers' minds, because it always does when extreme weather patterns get this intense. So let's address it directly, even though it's going to take a slight detour through some uncomfortable territory. Part 10. The Energy Budget Reality Check. Whenever extreme weather patterns get this intense, certain ideas start circulating online. You've probably seen them. Speculation that the weather isn't natural, that something, some agency, some technology, some hidden program is manipulating the atmosphere, intentionally generating these extremes for reasons that range from research to malice. I want to address this directly, because the science here is actually pretty clear, and ignoring the speculation doesn't make it go away. It just leaves people confused. The atmosphere is a system that operates at energy scales that are almost incomprehensibly large. A single mid-sized thunderstorm releases somewhere on the order of 10 to the 15th joules of energy over its lifetime. A major hurricane releases around 10 to the 20th joules over its full life cycle. The total kinetic and thermal energy of the atmosphere at any given moment is on the order of 10 to the 22nd joules. That's a 1 followed by 22 zeros. To put that in perspective, the entire global energy production of human civilization, summed across every power plant and industrial facility on Earth, runs at around 10 to the 20th joules per year. The atmosphere contains, in a single moment, more than 100 times the energy that humanity produces in an entire year. The technologies that occasionally get accused of weather manipulation operate at scales that aren't even close. Cloud seeding, which is real and has been studied extensively for decades, can modify the precipitation efficiency of clouds that are already going to produce precipitation. It cannot create storms from nothing. It cannot move atmospheric features around. It can squeeze a few more percentage points of rainfall out of an already raining cloud in localized areas under specific conditions. The total energy involved is trivial compared to the energy in the storm itself. HAARP, the High-Frequency Active Auroral Research Program in Alaska is the favorite target of weather control speculation, but the actual capabilities of the facility don't match the mythology. HAARP heats a tiny patch of the upper ionosphere with focused radio waves for research purposes. The energy involved is on the order of a few megawatts, which is about the output of a small power plant. The atmosphere routinely processes that much energy in random thunderstorms over the course of a few minutes. The idea that HAARP could lock a Rossby wave across an entire continent for 2 weeks would require it to be operating at energy levels millions of times higher than its actual output in a geographic location nowhere near where it sits. The reason these narratives recur during extreme events is psychologically interesting and worth understanding. When the weather is doing something genuinely strange, like the dipole we have now, there's a natural human desire to find an agent behind it, someone responsible, some intentional cause. The idea that an atmosphere this powerful could just spontaneously organize itself into a pattern this extreme, with no one in charge, can feel intolerable. So, narratives emerge that put someone in charge, even if the someone is sinister. It's almost more comforting to believe in malicious weather control than to accept that the system is running itself. But the system is running itself. The locked Rossby wave we're observing is being maintained by the dynamical interactions we discussed earlier, the wave amplitude feedback, the MJO support, the positive PNA, the closed low anchoring. None of those processes require any external input from human technology. They've been observed and documented in atmospheric records going back over a century. The current event is unusual, but it's not unprecedented. It fits the profile of patterns that have occurred before, just rarely. The fact that the pattern is internally driven actually makes it more interesting, not less. It tells us that the Earth's atmosphere is capable of organizing itself into configurations of this intensity without any push from outside. It tells us that the natural variability of the system is wider than our day-to-day experience suggests. And it raises questions we're going to come back to in the final act of this video about whether what we're seeing now is a one-off or a glimpse of a new kind of normal. The atmosphere is doing this on its own, and it's not finished. Part 11: The Incoming System, Monday through Wednesday. Let's talk about what's coming next, because the next system in this sequence is already loading in the model output. The forecast for Monday into Tuesday and Wednesday across the central United States is beginning to converge on a setup that looks structurally similar to last week's outbreak, but with a few important differences. The atmospheric models are showing a new disturbance moving into the locked pattern from the west, embedded in the same southwest to northeast flow that's been steering features across the country for the past 2 weeks. This isn't a new pattern. It's the next cycle of the existing pattern. The structure of the incoming system is what meteorologists call a dual low-pressure setup. There's a primary surface low forecast to develop over the Central Plains by Tuesday morning, and a secondary low that may form along the Gulf Coast or develop out of an old frontal boundary further south. When you have 2 low-pressure centers like this, in proximity but not yet merged, the atmosphere has a few different options for how the system can evolve. The 2 lows can stay separate and produce 2 different storm tracks. They can merge into a single deeper system, or they can engage in a process called phasing, where they don't fully merge but interact strongly enough to amplify each other. The phasing scenario is the one forecasters are watching most carefully because it tends to produce the most intense, severe weather outcomes. The wind shear forecast for Tuesday and Wednesday is significantly stronger than what we saw in some phases of last week's outbreak. Both deep layer shear, which is the change in wind from the surface to about 30,000 feet, and low-level shear, the change in the lowest few thousand feet, are projected to reach values that strongly favor supercell development. Storm relative helicity values, which measure how much rotation is available for storms to ingest into their updrafts, are forecast to climb into the range associated with strong tornado risk. The geographic corridor for this system is also expanding compared to last week. The earlier outbreak was concentrated in the southern plains and the Mississippi Valley. The Tuesday and Wednesday system is forecast to put severe weather risk across a much broader area from North Texas all the way up through Oklahoma, Kansas, Missouri, into Arkansas and parts of Tennessee, with risk extending even further east into the Ohio Valley and parts of the Tennessee Valley by Wednesday. That's a corridor of severe weather risk that stretches more than 1,000 miles. Not all of that corridor will see equal threat. The highest risk areas are still being refined as the models update, but the spatial extent of the threat is significantly larger than what we saw last week. The connection to the existing baroclinic boundary is what makes this system so concerning. We talked earlier about how the same boundary that produced the April outbreak is still in place across the southern United States, currently driving the Gulf flooding. As the new disturbance moves into that boundary, it's going to encounter all the ingredients that have been building up there for the past several days. The boundary is sharp, the moisture is high, the instability is primed. The new system isn't bringing new severe weather ingredients with it, it's simply triggering the ingredients that are already in place. This is a really important distinction, and it's one of the reasons forecasters are paying close attention. In a typical severe weather setup, you have a system that travels across a region, briefly tapping into local instability before moving on. The instability gets used up, the atmosphere has to recover. But in a setup like the one developing for Tuesday and Wednesday, the instability isn't going anywhere. It's been parked over the same region for days. The new system is just triggering it. And once the trigger is pulled, the response can be much more intense than what you'd see in a comparable setup with less preconditioning. The timing is the other piece I want to flag. The system arriving Tuesday and Wednesday is going to overlap with the still active Gulf flooding. Some of the same regions that are dealing with high water from the current event are going to be at risk for severe storms from the new event. That kind of compound hazard scenario, flooding plus severe weather, in the same geography within a few days of each other, is exactly the kind of compounding I want you to keep in mind, because we're going to come back to it. The hazards forecast for the new system include all three categories of severe weather. Damaging winds are likely, with potential gusts in the 70 to 90 mile per hour range in the strongest cells. Severe hail is forecast, with stones 2 inches or larger in the areas with the highest cape and shear overlap, and tornadoes are on the table, including the possibility of strong tornadoes EF2 or higher in the most favored zones. But here's the framing I want you to take away from this section. This isn't a separate event from the rest of the pattern we've been discussing. It's not a new system arriving to surprise us. It's the next scheduled output from a machine that's been running continuously for over a week. The atmospheric model forecasts converging on this setup are basically just confirming what the locked Rossby wave structure has been telling us all along, that the pattern is going to keep producing major events as long as it remains anchored. Tuesday and Wednesday are simply when the next round comes due. The way the system is going to organize itself in the lead up to Wednesday is worth tracking carefully, because Tuesday is when the alignment phase happens. Part 12, Tuesday, the setup. Tuesday's setup is what forecasters call a transition day. The atmosphere is in the process of organizing itself for what comes next, and the storms that fire on Tuesday are themselves both significant hazards and indicators of how the larger system is shaping up. Think of it as the system clearing its throat before it speaks. The geographic corridor for Tuesday extends from North Texas through Oklahoma and Kansas into Missouri and possibly reaching into the lower Ohio Valley by late evening. This is a 1,000-mile long zone where afternoon and evening thunderstorms are likely to fire as the new disturbance moves into the warm sector. The storm initiation zones, the specific places where the first cells are most likely to form, are concentrated along old frontal boundaries that have been hanging around from previous systems and along the leading edge of the incoming dry line as it pushes into the moist Gulf air mass. The primary hazards on Tuesday are forecast to be wind and hail, with tornado risk present but generally lower than what's expected for Wednesday. The reason for the wind-hail dominance has to do with the storm mode that's most likely to develop. With the dry line serving as the primary trigger, and shear values that favor multi-cell and high precipitation supercell modes more than discrete classic supercells, the storms that form Tuesday are likely to organize into clusters and lines rather than staying as isolated rotating cells. Linear and clustered storm modes are more efficient at producing widespread damaging winds and large hail than at producing strong tornadoes. You can still get tornadoes embedded in lines. They happen all the time, but the most violent tornadoes typically come from discrete supercells, and Tuesday's environment is somewhat less favorable for those. The atmospheric preconditioning is doing a lot of work here. We've talked about the warm sector being primed with moisture and instability for days. By Tuesday, that preconditioning is going to have been ongoing for over a week. CAPE values in the heart of the warm sector are forecast to climb above 3,500 joules per kilogram in some areas, which is the kind of instability that supports very tall, very intense convective updrafts. Strong updrafts are what produce giant hail because they hold ice particles aloft long enough for them to grow into golf ball, baseball, or softball-sized stones before falling. There's a feature in Tuesday's forecast that I want to highlight because it's the kind of detail that often gets overlooked but ends up mattering. The residual boundaries from the storms that fire Tuesday afternoon and evening are likely to influence where the more intense storms form on Wednesday. Outflow boundaries from decaying thunderstorm complexes are essentially miniature cold fronts that propagate away from dying storms, and they often serve as focal points for the next round of severe weather. If Tuesday's storms produce strong outflow boundaries that drape across the Mid-South and Tennessee Valley overnight, those boundaries can become the trigger zones for Wednesday's main event. This is what I mean when I say Tuesday is the alignment phase. The storms that fire Tuesday aren't the climax. They're the system organizing itself. They're the boundaries getting laid down that Wednesday's storms are going to exploit. They're the moisture getting redistributed in patterns that determine where the highest CAPE will be on Wednesday afternoon. The atmosphere is essentially doing pre-game positioning, and the placement of features at the end of Tuesday is going to substantially influence what happens on Wednesday. The locked pattern is what's allowing all of this to happen. In a more progressive flow regime, Tuesday's features would get swept out of the area before Wednesday morning, and Wednesday would start fresh with whatever new disturbance arrived. But the locked pattern is keeping the boundaries in place. The features that organize on Tuesday are still going to be there Wednesday morning, providing focused targets for the next round of convection. It's another expression of the same dynamic we've been tracking all along. The pattern isn't moving, so the features inside it accumulate rather than disperse, and each new round inherits the legacy of the previous one. For viewers in the affected regions, Tuesday is the kind of day where the threat is real but the headline event is still pending. There will likely be tornado warnings, severe thunderstorm warnings, flash flood warnings. There may be significant damage, but the meteorological community is going to be watching Tuesday primarily as a setup day for what comes next. And what comes next is potentially the most dangerous weather day of this entire pattern so far. Break time, Moats, Part 13 Wednesday, the wild card. Wednesday is where the wild card sits. The Wednesday risk window is forecast to focus on a region of the country that meteorologists informally call Dixie Alley, the part of the southeastern United States, mostly Alabama, Mississippi, parts of Tennessee, Arkansas, Louisiana, and northern Georgia, where some of the most violent and dangerous tornado outbreaks in American history have occurred. Dixie Alley isn't part of traditional Tornado Alley, which sits further west across Texas and Oklahoma, but in many ways the tornadoes that hit Dixie Alley are more dangerous because they tend to occur in environments with more moisture, more cloud cover, and at times of day, including overnight when warning lead times become shorter and protective action becomes harder. The setup for Wednesday is what forecasters call conditional. That means whether the worst-case scenario actually plays out depends on a few specific factors aligning, and there's still uncertainty about whether they will. The first factor is instability recovery. After Tuesday's storms move through the region, the atmosphere needs to destabilize again, meaning the warm, moist air at the surface needs to reload, and the temperature lapse rates aloft need to remain steep enough to support strong updrafts. The current model forecasts suggest that recovery is going to happen, but the magnitude of the recovery is uncertain, and weaker recovery would mean a less intense outbreak. The second factor is boundary positioning. The location of any residual outflow boundaries from Tuesday's storms is going to determine where the highest tornado potential sits on Wednesday afternoon and evening. If the boundaries end up draped across central Mississippi or northern Alabama, the tornado risk in those specific zones could be very high. If they end up further south or further north, the geography of the risk shifts. Forecasters are watching boundary placement obsessively because small differences in position can mean the difference between a contained event and a major outbreak. The tornado potential for Wednesday, if all the conditional factors align, is genuinely high. Wind shear is forecast to be strong. Storm relative helicity is forecast to support tornadic supercells. Surface-based instability is forecast to be sufficient. The combination of those ingredients in Dixie Alley, particularly during the late afternoon to early overnight period, is exactly the kind of setup that has produced historic outbreaks in the past. Outbreaks like April 27th of 2011, when a single afternoon and evening produced over 50 tornadoes across Alabama and surrounding states, including multiple violent EF4 and EF5 tornadoes that killed hundreds of people. The Wednesday setup isn't necessarily a parallel to that event in scale, but it's structurally in the same family of high-end Dixie Alley setups. The nocturnal risk factor is one of the things that makes Dixie Alley setups particularly dangerous. Tornadoes that occur after sunset are roughly twice as deadly, statistically, as tornadoes that occur during daylight hours. The reasons are: intuitive people are sleeping, warning systems are harder to hear, visual confirmation is impossible, and many people in the affected regions live in mobile homes or other structures with limited tornado shelter. The current Wednesday forecast has the threat extending well into the evening and overnight hours across parts of the Mid-South and Deep South, which is exactly the time of day when fatality rates per tornado tend to spike. There's significant uncertainty in the Wednesday forecast, whether the conditional factors align, whether the storms that fire Tuesday undermine Wednesday's instability or enhance it, whether the timing of peak instability matches the timing of peak forcing. All of those questions are going to be answered in the next 48 hours by additional model runs and real-time observations. But the potential, the upper bound of what the system could produce on Wednesday is genuinely concerning. We could be looking at the second major severe weather outbreak in 2 weeks in a different geography from the same locked pattern. The forecaster attention being paid to Wednesday reflects this. The Storm Prediction Center is highlighting the day in their extended outlooks. National Weather Service offices in the affected regions are starting to post preliminary briefings. Local emergency management agencies are reviewing their notification protocols. The warning is going out several days in advance that a significant severe weather event is possible. Whether it materializes at the high end of the forecast envelope or the lower end, Wednesday is going to be a high-focus day for the meteorological community. And here's the connection back to where we started. 2 major severe weather outbreaks in 2 weeks across overlapping geographic regions, driven by the same locked Rossby wave pattern. That's not coincidence. That's the signature of a system that's still operating at full power, producing its second major energy release on a roughly 2-week cycle. The first cycle gave us April 23rd through 28th. The second cycle is loading for next week. And if the pattern persists through mid-May, as the Climate Prediction Center is forecasting, there's a real question of whether a third cycle could follow. The stakes here aren't theoretical. They're measured in lives, property, and the operational capacity of the people we depend on to warn us when these events are coming. And the pattern that's producing them, as we're about to see, isn't showing any sign of resetting. Part 14. The pattern isn't resetting. The Climate Prediction Center, which is the long-range forecasting arm of the National Weather Service, has been issuing extended outlooks for the next couple of weeks, and the pattern they're describing is striking in its consistency. The outlooks call for below-average temperatures across the eastern half of the United States, with above-average temperatures across the western half persisting through at least mid-May. That's the same dipole pattern we've been describing throughout this video, projected forward. The agency isn't forecasting a return to normal, they're forecasting the continuation of the abnormal. The reasoning behind the CPC outlook, when you read the technical discussion, is essentially the same dynamical reasoning we've been working through. The locked Rossby wave is expected to hold its position. The supportive teleconnections, the MJO and the PNA, are expected to remain in configurations that reinforce the locked pattern. The closed low anchoring the pattern is expected to remain anchored. There's no major upstream disturbance on the horizon that would have the energy required to break the configuration loose. So the forecast just runs the current pattern forward, day by day, through the middle of the month. That's a really significant statement when you stop to think about it. The CPC doesn't issue these kinds of confident extended forecasts lightly. Their outlooks are usually probabilistic, with confidence intervals reflecting the inherent uncertainty of forecasting weather more than a week out. When they issue an outlook with high confidence, as they have for the dipole pattern through mid-May, it means the dynamical signal is strong enough to overcome the normal noise that would otherwise dominate at that lead. Time, the lack of progressive flow, is the key indicator. In a more typical spring, you'd expect the jet stream to be in a generally progressive configuration, with waves moving steadily eastward and individual patterns lasting only a few days at a time. The progressive flow keeps the atmosphere mixed up, prevents any one configuration from dominating, and maintains a kind of statistical normality, even when individual events are extreme. What we have instead is a stuck configuration that's allowing the same pattern to persist day after day, week after week, with no sign of the progressive flow returning. The ensemble agreement on this forecast is what makes it especially compelling. When forecasters look at extended range model output, they don't just look at one model run. They look at ensemble's multiple runs of the same model with slightly different starting conditions, plus runs from different models entirely. If the ensembles diverge widely, it means the forecast is uncertain, because small differences in the initial state of the atmosphere are producing big differences in the projected outcome. If the ensembles converge, meaning most or all of the runs are showing similar outcomes, it means the dynamical signal is strong enough to overcome the noise. The current ensembles are showing strong agreement on pattern persistence. Most of the European model runs, most of the American model runs, and the consensus of major ensemble systems are all showing the locked pattern holding through at least the next 10 days, with some runs extending pattern persistence even further. That kind of agreement is unusual for this lead time, and it's part of why the CPC is comfortable making the call they're making. Now, I want to be careful here, because there's a difference between a pattern holding for 2 weeks and a pattern holding indefinitely. The atmosphere is a chaotic system, and even the most strongly supported configurations eventually break down. The locked pattern we're observing will, at some point, transition to something else. The question is when, and whether the transition is gradual or abrupt, and what comes next. The multi-week regime signal that's emerging from the data suggests this isn't going to break down on the typical pattern timescale of 5 to 7 days. We're already past that timescale, and the pattern is showing no sign of weakening. The next plausible breakdown timeframe, based on the typical life cycles of similar configurations in the historical record, is in the 2 to 4 week range. If the pattern holds that long, it'll be among the more persistent atmospheric blocking events in recent decades. Here's the framing I want to leave you with for this section. Most severe weather events, even big ones, are transient. They show up, they do damage, they leave. The atmosphere returns to something like normal, and people start cleaning up and moving on. What we're dealing with now isn't transient. The system is not cycling, but it's holding. The events we've already seen, and the events forecast for next week, are not separate stories. They're outputs of a single configuration that's refusing to dissipate. That insight matters because it changes how you should think about the cumulative impact of what's happening. And the cumulative impact is where things get really concerning. Part 15: Repetition Risk. When the same atmospheric pattern produces multiple major events over a multi-week period, the damage from those events doesn't just add together arithmetically, it compounds. Soil saturation is the most obvious example. When a region gets hit by a major flooding event, the ground absorbs as much water as it can, but there's a limit to that absorption capacity. After the soil saturates, any additional rainfall runs off immediately into streams and rivers that are already full from the previous event. So the second flood event in a sequence doesn't have the soil to act as a buffer the way the first event did. Rainfall amounts that wouldn't normally cause major flooding become catastrophic because they're falling onto a landscape that has no capacity to absorb them. The Gulf Coast and the Mid-South, both of which are currently dealing with significant flooding, are exactly the regions that are forecast to be at risk for severe weather and additional rainfall in the Tuesday and Wednesday system. The next round of rain isn't going to find dry ground. It's going to find saturated soil, full reservoirs, and stressed flood control infrastructure. The hydrological response to comparable rainfall amounts is going to be much more severe. Infrastructure stress is another compounding factor. Power grids that have been damaged by one storm event are weaker against the next event. Trees that were partially uprooted but didn't fall in the first event are more likely to fall in the second one. Roof structures that took partial hail damage in the first event are more vulnerable to subsequent hail. The cumulative effect across multiple events can be significantly larger than the effects of the individual events would predict. The repeat hit regions are particularly vulnerable. Take parts of southeast Oklahoma, North Texas, and Arkansas, areas that took hits during last week's outbreak and are now in the projected risk zone for next week's system. Communities that are still in the early stages of cleanup from one event are not prepared to absorb a second event. Insurance adjusters haven't completed their assessments. Building permits for repairs haven't been issued. Materials and contractors are in short supply. A second event in the same area, before the first has been substantially recovered from, can functionally double or triple the damage, rather than just adding to it. Recovery time compression is the technical term for what's happening here. Communities normally have weeks or months between major weather events to get back to baseline before the next one hits. When the time between events compresses to days, the recovery process gets interrupted and the cumulative impact accelerates. Federal emergency management resources get spread thinner. State and local response capacity gets exhausted. The same crews who were in the field after last week's tornadoes are going to need to be in the field again next week, with fatigue building up across multiple events. The economic and insurance impact is something I'll mention briefly, because it deserves more attention than I can give it in the time we have. The insurance industry models pattern-based events differently than they model isolated events, and a multi-week pattern of high-impact weather across overlapping regions can produce loss totals that exceed the modeled reserves for the region. That has knock-on effects on insurance availability, premiums, and the long-term economic health of affected communities. We're not at the catastrophic level of those impacts yet, but a sustained pattern through mid-May with multiple major events could push toward thresholds that matter at the regional economic scale. The framing I want you to take from this is that damage compounds faster than weather resets. When the pattern is locked and producing multiple events on a short cycle, the system as a whole, meaning communities, infrastructure, response capacity, falls behind. Each event leaves things in slightly worse shape than the last one found them, and the gap between resilience and exposure widens. This is what I mean when I say the central thread connects everything. The persistence of the pattern isn't just about meteorology, it's about how the meteorology interacts with the human and built systems that have to absorb the impacts. A 2-week pattern of extreme weather in the same general regions is fundamentally different from a series of unrelated events spread out over a longer period, because the compounding dynamics change everything, which raises the question that's been hanging over this entire video, the one we have to confront head-on now. If this isn't a typical pattern, and it isn't a typical event sequence, then what exactly is it? What are we actually looking at? Part 16: Pattern versus Regime. Here's where the science gets harder, and where I have to be careful with what I tell you, because the honest answer involves a lot of uncertainty. There's a meaningful distinction in atmospheric science between a pattern and a regime. A pattern is a temporary configuration, an arrangement of features that lasts for a few days or a few weeks before transitioning to something else. Patterns come and go. They're the basic unit of weather. A regime is something larger and more persistent, a baseline configuration that biases the kinds of patterns that emerge. Regimes can last for months, seasons, or longer, and they shape the statistics of what's normal in a given period. Most events get classified as patterns. The vast majority of unusual weather episodes, even severe ones, are captured by the pattern framework. They happen, they end, and the long-term climate baseline keeps doing what it was doing before the event. The pattern is anomalous, but the regime, the baseline against which the anomaly is measured, remains stable. But occasionally, an event is persistent enough or unusual enough that it raises a different question. Not just whether the pattern is unusual, but whether the regime itself is shifting, whether the baseline statistics that we use to define normal are themselves changing, with the result that what looks like an anomaly today might become more typical tomorrow. The duration threshold that separates a pattern from a possible regime change is fuzzy, but somewhere around 10 to 14 days is when forecasters start to take the regime question seriously. We're approaching that threshold right now. The pattern that produced last week's outbreak has now been operating, in some recognizable form, for about 10 days. If it persists through mid-May as forecast, we'll be looking at a duration of 3 weeks or more. That's well into the territory where the question of regime versus pattern becomes legitimate, and meteorologists who study atmospheric variability start asking it seriously. There's a concept called atmospheric memory that's relevant here. The atmosphere, as a chaotic system, technically loses predictability after about 2 weeks. That's the limit of detailed deterministic forecasting. But the underlying patterns that bias the atmosphere's behavior can persist much longer than 2 weeks, and they can leave imprints on subsequent weather even after the original pattern dissipates. A locked Rossby wave that lasts 3 weeks doesn't just produce 3 weeks of unusual weather, it can shift the surface temperature distribution, change soil moisture patterns, alter ocean surface temperatures in adjacent waters, and modify the atmospheric conditions that form the starting point for subsequent patterns. The atmosphere remembers, and the memory shapes what comes next. Comparing the current event to past pattern locks gives us a sense of where it might fit historically. The May 2020 event I mentioned earlier produced a similar dipole, but it didn't last as long. The summer of 1980 produced a long-lasting heat dome over the central United States that contributed to the Dust Bowl-style drought of that year, and elements of that pattern resemble the current Western Ridge. The winter of 1977 had a remarkably persistent eastern trough that produced one of the coldest winters of the 20th century in the eastern United States. None of those analog cases is a perfect match, but they all involve patterns that persisted significantly longer than typical and left lasting imprints on the climate of their year. The question of whether May 2026 is going to redefine seasonal norms or just be another notable but transient event is one we genuinely don't know the answer to yet. We're in the middle of it. The data isn't all in. The breakdown of the pattern, when it eventually happens, is going to teach us a lot about which category this event belongs to. If the pattern dissipates cleanly and the atmosphere returns to a normal progressive flow regime in the second half of May, we'll likely categorize this as an unusual but ultimately transient pattern. If the pattern dissipates and a new but similar configuration replaces it, we might be looking at something more like a regime that's expressing itself through multiple individual patterns. There are competing interpretations that I want to present without taking sides, because the science here doesn't yet support a strong conclusion. One school of thought, which has significant support in the atmospheric science community, sees events like this as being within the range of natural variability for the atmosphere. The atmosphere has always produced occasional pattern locks, and the current event might just be a particularly impressive example of a phenomenon that's been part of the system all along. We're more aware of it now, because of better observation systems and faster information dissemination, but it's not necessarily new. Another school of thought, also well supported, sees an increase in the frequency or persistence of high-amplitude wave patterns over the past several decades. According to this view, something is changing in the underlying system that's making locked patterns more likely. Whether that change is driven by long-term climate variability, by anthropogenic influences, or by some combination, the result is that we should expect more events like this one in the coming years, not fewer. The honest answer is that we don't have enough data to definitively distinguish between these interpretations yet. The historical record of atmospheric blocking events isn't long enough or detailed enough to make robust statistical statements about whether the frequency is increasing in a way that exceeds natural variability. The current event is consistent with both interpretations. We won't know which one is closer to right until we have more events, more years of data, and more refined analytical tools. What I can tell you is that the question matters. If we're in a regime where these kinds of events are becoming more frequent, then the infrastructure, agricultural practices, and emergency response systems that were designed around historical pattern statistics are going to be increasingly mismatched against the actual atmosphere. That mismatch produces costs, economic, social, sometimes human, that compound over time. Whether or not the current event is part of a regime change, the question of how we adapt to a possible regime change is becoming increasingly urgent. The tension I want to leave you with for this section is this. We're observing an event that's at the upper end of what the atmosphere typically produces. We don't yet know if it's a one-off or a glimpse of a new normal. The forecasts for the next few weeks are going to give us more data, but the data we have already raises questions that won't be answered for years and possibly decades as more events accumulate and the long-term statistical picture comes into focus. Which means we're not just watching a weather event, we're watching, possibly, a data point in a much longer story. Part 17. The Climate Signal Debate. The connection between atmospheric patterns like the one we're observing and the broader question of climate change is something I want to address directly but carefully. There's a hypothesis in climate science called Arctic amplification. The basic idea is that the Arctic region has been warming significantly faster than the rest of the planet over the past several decades. Polar amplification is a well-documented observation. The Arctic's surface temperature has risen at roughly twice the global average rate, and the warming has been particularly pronounced in fall and winter. The cause is a combination of factors, including the loss of sea ice, which exposes darker water that absorbs more solar radiation, changes in ocean circulation, and feedback loops involving water vapor and cloud cover. The hypothesis goes further, though. Some scientists argue that Arctic amplification is reducing the temperature gradient between the polar regions and the mid-latitudes. A weaker gradient, the argument goes, means a weaker jet stream, and a weaker jet stream is more prone to becoming wavy, with bigger ridges and deeper troughs. In other words, Arctic amplification might be making locked Rossby wave patterns more frequent by weakening the very gradient that normally keeps the jet stream flowing strongly from west to east. This is sometimes called the wavy jet stream hypothesis, or the Francis-Vavros hypothesis, after two of the scientists who developed it. The mechanism is theoretically plausible. The math works out in idealized models. And there have been some empirical studies that have found possible signals of increased wave amplitude over recent decades. But there are also significant counterarguments. Other studies have failed to find a robust signal of increasing wave amplitude. The natural variability of the atmosphere is large, and detecting a small trend against that variability requires very long datasets and very careful statistical methods. Some climate models predict increased wavy patterns under continued warming, while other models predict decreased wave amplitude. The scientific community is genuinely divided, and the debate is active. What I can tell you is that the kind of pattern we're observing now, a locked Rossby wave, producing simultaneous extreme cold, extreme heat, flooding, and severe weather across a wide geographic area, is exactly the kind of pattern the wavy jet stream hypothesis predicts should be more common in a warming Arctic. The current event doesn't prove the hypothesis. A single event can't prove anything in climate science. But the current event is an example of the kind of pattern the theory predicts should be increasingly likely. I want to be very clear here, because this is exactly the kind of topic where it's easy to overreach. We can't attribute this specific pattern to climate change. The methodology for attributing individual weather events to climate change is improving rapidly, but it requires extensive analysis with multiple climate models, comparing the probability of an event in a world with current greenhouse gas concentrations versus a hypothetical world without them. That kind of attribution analysis hasn't been done for this event, and even when it is done, the results are usually probabilistic rather than definitive. They tell you that an event was, say, 3 times more likely under current conditions than under pre-industrial conditions, not that it would or wouldn't have happened either way. What we can say is that events like this one are consistent with the expectations of theories about how a warming climate would affect mid-latitude weather. We can also say that they're consistent with natural variability, because individual events almost always are. The path forward, scientifically, involves accumulating more events, refining the theories, and continuing to test them against observations as the climate continues to evolve. We're decades, possibly generations, away from being able to look back at this period and say with confidence whether events like the May 2026 pattern were the leading edge of a new regime, or just particularly impressive examples of natural variability, which means the current event sits in a peculiar epistemic position. It's a data point in a debate that's far from settled, and how we ultimately interpret it depends on what comes next. If we see more events like it over the next 5 or 10 years, the regime change interpretation gains support. If events like this remain rare, the natural variability interpretation gets reinforced. We're collecting evidence in real time, and the conclusion is going to take a long time to crystallize. The connection to our central thread is that the current pattern is at minimum a candidate for being an example of the kind of high-amplitude, persistent wave pattern that some theories predict should become more common. Whether or not it ultimately turns out to be such an example, it's behaving like one right now, and the impacts are real, regardless of how the long-term debate plays out. Part 18. ENSO. Background, influence. There's a background condition I want to mention briefly, because it's part of the larger picture, even though it's not the primary driver of what we're seeing. The El Niño Southern Oscillation, abbreviated ENSO, is the climate pattern centered on the equatorial Pacific that affects weather around the world. ENSO has 3 phases: El Niño, La Niña, and neutral, and the current state is in transition from a recent La Niña toward neutral conditions. The Oceanic Niño Index, which is the standard measure of ENSO state, has been shifting from around -0.55 toward -0.16 over the past several months, indicating a relaxation of La Niña conditions and a movement toward the neutral phase. ENSO affects severe weather in the United States in some specific ways. Neutral phases, particularly in the spring, tend to be associated with above-average severe weather activity in the Central Plains, because the relaxation of either El Niño or La Niña constraints allows the atmosphere to fall into more variable patterns that include occasional high-amplitude wave events. The geography of severe weather during ENSO-neutral periods tends to focus more on the southern plains and mid-south, which is exactly where last week's outbreak concentrated and where next week's system is forecast to develop. I don't want to overstate the role of ENSO here. The locked Rossby wave pattern we've been discussing isn't being driven by ENSO directly. The MGO and the PNA are doing most of the heavy lifting on the synoptic scale, but ENSO operates as a background condition that biases where the energy gets released. It's the difference between, say, a severe weather pattern that focuses on Texas and Oklahoma versus one that focuses on Iowa and Wisconsin. Both are possible outputs of similar synoptic patterns, but ENSO state tilts the probability one way or the other. The current shift toward ENSO neutral, with continued weak La Niña residuals, fits well with the geographic concentration we've seen in the event so far. The April outbreak focused on the southern plains. The current Gulf flooding is concentrated along a southern boundary. The forecast severe weather for next week is also focused in that southern corridor. All of those geographic concentrations are consistent with what ENSO-neutral spring patterns historically favor. So while ENSO isn't the cause of the locked pattern, it's contributing to the wear of the impacts. Different ENSO states would produce different geographic distributions of severe weather, even within the same broader synoptic configuration. The current ENSO state is amplifying the focus on the southern United States, which is where most of the major events have hit. For now, the connection back to the central thread is that ENSO is one of the background conditions shaping where the locked pattern releases its energy, even though it's not driving the pattern itself. The atmosphere's choices about where to throw its biggest punches are being influenced by ENSO state, while the strength and persistence of the punches themselves are coming from the locked Rossby wave configuration. Background condition plus locked pattern equals geography of impacts. Part 19. The solar geomagnetic distraction. Now, before we get to the final section, I want to address one more thing that tends to come up in conversations about extreme weather events, because it's been circulating online in connection with the current pattern. There was a minor geomagnetic storm earlier this week, classified as a G1 event on the Space Weather Prediction Center's 5-level scale. G1 is the lowest category of geomagnetic storm, meaning it had measurable but minor impacts on Earth's magnetic field. Some auroras at high latitudes, some minor disruptions to satellite operations, nothing catastrophic, nothing close to it. Whenever a geomagnetic event occurs in temporal proximity to extreme weather, you can count on speculation appearing online connecting the two. The argument usually goes something like this: solar activity affects Earth's atmosphere, geomagnetic storms inject energy into the upper atmosphere, and therefore the geomagnetic activity must be driving the extreme weather we're seeing. The science here is straightforward, even if the speculation isn't. There are some documented connections between solar activity and atmospheric patterns, but they operate on much longer timescales than the timing of individual storms. The solar cycle, which lasts roughly 11 years, has measurable effects on stratospheric circulation, which can in turn affect tropospheric weather patterns. Major solar events, like X-class flares and large coronal mass ejections, can have detectable atmospheric effects, but the effects are subtle and concentrated in the upper atmosphere, far above where weather happens. The mismatch in timescales is the key issue. Geomagnetic storms typically last hours to days. Atmospheric patterns like the one we're observing develop and persist over weeks. The kind of locked Rossby wave configuration we have right now requires sustained dynamical forcing, which a brief geomagnetic event simply can't provide. The energy injected into the upper atmosphere by a G1 storm is significant on its own terms, but it's many orders of magnitude smaller than the energy required to maintain a continental-scale wave pattern. And the recent geomagnetic storm wasn't accompanied by any major coronal mass ejection or X-class flare. It was a relatively minor event in solar terms. The solar conditions that have been argued to potentially affect weather in research that's still actively debated are major events like the Carrington event of 1859 or comparable storms. We haven't had anything close to that scale of solar activity recently. The current solar cycle is approaching its peak, but the activity has been moderate rather than extreme. So the geomagnetic activity isn't a driver of what's happening in the lower atmosphere. The atmospheric pattern we're observing is being driven by the dynamical processes we've discussed throughout this video: the Rossby wave mechanics, the teleconnection support, the baroclinic gradient, the moisture supply. Those are the things to watch. The solar speculation, while interesting in its own right, is a distraction from the actual mechanisms that are producing the events we're seeing. The reason I bring it up at all is to be transparent about the various theories that are circulating, and to give you the tools to evaluate them. The atmosphere is a complex system with many inputs, and it's reasonable to wonder how all of those inputs interact. But the dominant signal in the current event is the locked atmospheric pattern itself. The solar contribution, if any, is in the noise. Which brings us back, finally, to where we started, to the question that's been hanging over this entire video. Part 20 final frame. The system is still running. Let's recap what we've established, because the picture that emerges, when you look at it whole, is genuinely remarkable. Phase 1 of this pattern produced the April 23rd through 28th severe weather marathon, 97 tornado reports, the EF4 in Enid, Oklahoma, the 95 warnings in a single day from St. Louis, over 1,500 warnings issued by the National Weather Service across 6 days, a near miss in terms of fatality count, but a maximum effort in terms of atmospheric output. Phase 2 is what we're living through right now. The continental temperature dipole splitting 50s in Texas from 80s in Seattle, the 65 active flood warnings strung across the Gulf Coast, the freeze warnings stretching from the upper Midwest to the mid-Atlantic, the training convection along the same baroclinic boundary that drove last week's tornadoes, the same machine expressing itself in different modes across different geographies. Phase 3 is loading right now. The Tuesday and Wednesday system, embedded in the same flow, is pulling into the same boundary that's been hosting all the previous activity. The atmospheric ingredients are positioned. The shear is forecast to be strong. The cape is forecast to be high. The geographic corridor is wide, and the Wednesday-Dixie Alley risk has the potential to deliver a second major outbreak in a different region from the same locked pattern. Beyond Phase 3, the Climate Prediction Center is forecasting the dipole to persist through at least mid-May. That implies a Phase 4 and possibly a Phase 5 in the form of additional events that haven't yet shown up clearly in the forecast guidance, but are dynamically supported by the persistence of the configuration. The atmosphere doesn't have to produce identical events in each cycle. It can shift the geography, it can shift the hazard mode, but as long as the locked pattern holds, the energy keeps flowing, and the energy has to go somewhere. The continuity across all these phases is what makes this event different from a typical sequence of severe weather episodes. We're not looking at a string of unrelated outbreaks driven by different upstream features. We're looking at a single configuration producing multiple outputs, each of which inherits the legacy of the previous one. The reload cycles aren't independent, they're connected through the persistent geometry of the locked Rossby wave and the supporting teleconnections that keep it locked. The unresolved question is how many cycles are going to occur before the pattern breaks down. The answer depends on factors we can model but can't perfectly predict: when the MGO will move out of its current supportive phase, when the PNA will weaken, when an upstream disturbance will accumulate enough energy to disrupt the closed low anchoring the trough. Forecasters are tracking all of these factors in real time, and the answer will become clearer as we get into mid-May. But right now, looking forward, the pattern is showing every sign of producing at least one or two more major events before it transitions to something else. The framing I want to leave you with is that May 2026 is not a completed story. It's a story in progress. The events we've already seen, dramatic as they are not the conclusion. They're chapters in a longer narrative whose ending hasn't been written yet. The Tuesday and Wednesday system is going to add another chapter. What comes after that is dynamically supported, but not yet forecast in detail. This is one of the reasons the meteorological community is paying such close attention to this event in real time. We're not just observing impacts after the fact. We're watching a major atmospheric event unfold in something close to real time, with the ability to ask questions about its mechanics and implications as it's happening. That kind of opportunity is rare, and the data being collected, observations, model verifications, impact assessments, is going to be studied for years. The lessons learned from this event will inform forecasting practices, climate research, and emergency preparedness across the country. For viewers in the affected regions, the practical implication is straightforward. Stay aware of forecasts, have a plan, take warnings seriously. The pattern is not going to break before mid-May. Multiple high-impact events are still possible. The cumulative stress on infrastructure and response systems is going to keep increasing. For everyone else, the implications are broader. The current event is a reminder that the atmosphere is capable of organizing itself into configurations that produce simultaneous extremes across continental scales. It's a reminder that the boundary between unusual weather and exceptional weather is permeable. And it's a reminder that the systems we depend on, agricultural, infrastructure, economic, are calibrated to historical statistics that may not be the best guide to what's coming. The atmosphere right now, on May 1st, 2026, is sitting in a configuration that hasn't released all its energy. The pattern is loaded, the boundary is sharp, the moisture is high, the shear is strong, the supporting teleconnections are aligned, the closed low is anchored. Everything that needs to be in place for additional major events is in place, and forecasters are not seeing any sign of imminent breakdown. So, when I ask, as I have throughout this video, what is this pattern building toward, the honest answer is that we don't know yet. We know the building is happening. We know the components are accumulating. We know the cycles are continuing. What we don't know is how many more cycles will occur before the configuration finally relaxes, or what the cumulative impact will be when the dust settles. That uncertainty is uncomfortable, but it's also where the science lives. Real-time observation of a major atmospheric event, with all the attendant unpredictability, is how we learn how the system actually works. The closed loops in the dynamics, the teleconnection couplings, the boundary persistence dynamics, all of these are being tested in real time by the atmosphere itself, and the answers we get from watching this event play out are going to inform how we understand and forecast similar events in the future. What I want you to take from this video, more than any single fact about the current pattern, is the recognition that the atmosphere doesn't always do what the calendar suggests it should. May is supposed to be a transition month, the harshness of winter behind us, the heat of summer ahead, with mild and gradually warming conditions in between. That's what May usually looks like. But the atmosphere isn't bound by what's typical. The atmosphere does what the dynamics tell it to do, and when the dynamics align in unusual ways, the result is an unusual May. We're in the middle of one of those Mays right now. Whether it ultimately gets remembered as a particularly impressive but transient event, or whether it gets remembered as the leading edge of something larger, will depend on what happens in the next 2 weeks and beyond. The data is being collected, the questions are being asked, and the atmosphere, with characteristic indifference to our preferences, is going to do whatever it's going to do. What we can do is pay attention, watch the forecasts, take the warnings seriously, understand that the events we're seeing aren't coincidental, aren't random, aren't disconnected. They're the outputs of a single configuration that's still operating, still loaded, still producing. The system that produced last week's outbreak, the system that's producing this weekend's contradictions, the system that's loading next week's threat. They're not 3 systems. They're one system, expressing itself across different days and different geographies, with the same underlying machinery driving every single output. And that machinery hasn't stopped. So as you go through your weekend, whether you're somewhere watching record cold, or record heat, or the rain that won't stop, or the freeze that shouldn't be happening, remember that what you're experiencing isn't an isolated weather event. It's a chapter in a story that's still being written by an atmosphere that's still organizing energy, still focusing it through the same locked geometry, still preparing whatever cycle comes next. The atmosphere has not stabilized. It has paused between releases, and somewhere, right now, in the upper troposphere over the central United States, the next pulse is already building.